So Mo, what is mathematical inquiry?
Let me begin by saying something about the popular concept of mathematical inquiry. A large number of people think that mathematics is really, let me write that down, making calculations. So many people think
that's what you do in mathematics in school, right?
That's right. So if you get a number like 2, 4, 7, 8, 9, 7 plus 3, 9, 2, 6, and then you multiply that with 3, 6, 7, 2, whatever number. That they think that is making those calculations is mathematics. Mathematics can involve, and quite often does involve calculations, but that's not.
Okay. So yeah, so if this was mathematics, then Google would be the best calculator, or my computer would be the best
computer. That's right.
Yeah.
In fact,
best mathematician. So
that's right.
Best mathematician in the world would be.
Many mathematicians actually will not be able to do this correctly.
Yeah, I would guess most. It would be very long.
I don't think I can do that.
Yeah, I can't.
Yeah. The other popular conception is that it's about the real world. So they think, for example, that you have to buy, let us say, some apples, some pears, and you are given such and such amount, and then you give a, let's say 100 rupee or 500 rupee note. How much do you get back? So you're using calculations about the real world.
Yeah.
So many people think that math is really a science. Students don't realize that math is not a science.
People get a bachelor's in science and mathematics.
That's right.
Bachelor's of science in mathematics.
That doesn't make sense.
Yeah.
So here is the difference. Science is about the world we live in. The particular world that we live in. Math is about logically possible worlds.
What do you mean by logically possible?
Okay, so for example, in the particular world we live in, humans have 2 legs and 2 hands. But imagine a possible world in which humans have 16 legs and 5 heads. That is not logically impossible. That just doesn't happen to be true about this world. In this particular world, the attraction between 2 bodies, according to Newton, is inverse square law, gravitational attraction. But maybe there is a possible world in which the attraction is like inverse cube, or not even inverse. So math studies those worlds, logically possible worlds, of which our world happens to be just one of them.
So all that you mean is possible worlds, not the real world.
Right.
Okay.
This is sufficient, possible worlds, but why do we say some worlds are impossible? Because they are not allowed by logic. So math will not study a world in which the earth is flat and the earth is not flat. That is not logically possible, disallowed by logic. That's why I put logically possible, non-contradictory. And as we'll see, logic plays a huge part in the development of mathematics. So the question would be, how do you construct logically possible worlds? Mathematicians use axioms and definitions. Yeah, you can erase that. We create definitions, we use definitions to create objects. Objects like numbers, objects like triangles, circles, and so on. And we define them. So that means we have created those objects or relations or processes and so on. The axioms are about laws governing those objects. The laws of that world. Just as, for example, theory of laws of gravity and motion are about this world. these axioms are about the worlds that we are creating.
So when I saw the word axiom once, it was written that it's self-evident truths.
Right.
And what I saw was an axiom is an accepted but unproved statement.
Yes, that is another meaning. Accepted but unproved statement. Okay, to make sense of that, we have to take some examples of actual axioms. So there is an axiom, famous axiom in Euclid, that says, this is called the fifth postulate, which is also fifth axiom. Nowadays people don't distinguish between postulates and axioms. Euclid did, but for us it doesn't really matter. It says that there are many different ways of stating this. You can say if you have a line and a point outside it, it is always possible to draw exactly one parallel line. Now, this was taken to be a self-evident truth for several centuries. Euclid took it as a self-evident truth. And in the 19th century, people tried to prove it, and they discovered that you could construct different kinds of mathematics
If you get rid of this.
if you get rid of this and have some other axiom. So axioms are not self-evident truths. These are simply starting points, right? Not self-evident truths, but starting point. So that's why I said we create the worlds and we create these laws. And given these laws and given these objects,
What are the
what
logical
conclusions can you draw? That's why accepted for that world. But if you change a world,
then the axiom
the axioms will change. They are no longer accepted in some other world. So we could say, for example, given any finite line, AB in geometry, there is infinitely many points. That is one possibility. But there is an alternative possibility, given any finite line, there is a finite number of points.
Yeah.
If one of them is true, the other one cannot be true, right?
Yeah.
But in mathematics, you get two different mathematical worlds
Yeah.
by setting up these two axioms.
Yeah.
So this is right, accepted for the purpose of that world.
So once mathematicians create these worlds, then what do they do?
Then they see patterns in these worlds. So patterns. Just as we see patterns in the world that we live in, mathematicians see patterns, and they state these patterns as conjectures.
Okay.
Conjectures are statements that we think are likely to be true about these worlds, but now we have to prove them.
Okay.
So we prove the conjectures. When the conjectures are proved, they become theorems.
And what constitutes a proof?
Well, that we'll have to see. A proof is a kind of set of logical steps from these.
From the axioms and
Right,
definitions?
conclusions.
Yeah.
Set of propositions, set of steps that give you the conclusion, and that conclusion is a theorem. Exactly what it is we'll see in the course of
We saw a
illustrating
few in the last video,
That's right.
in the video comparing mathematics.
mathematics and science. Yes, we saw some of them, but today we'll see more of them. So what is a mathematical theory? Right. A mathematical theory in math has axioms, definitions, and the theorems deduced from those axioms. These are again about possible worlds. Yeah. That is a rough I think, description of what
Constitutes mathematics.
what constitutes mathematics.
What about something like mathematical modeling? Are you going to talk about that?
Yeah, mathematical modeling is when you take a mathematical theory and apply it to the real world.
Real world.
So, like when we go shopping and we buy, we give a 100 rupee note and we want change for various things we buy, that would constitute mathematical modeling. The calculations we do with that 100 rupee.
Yeah.
However, I think in the rest of the video we're not going to be talking about mathematical modeling. We'll touch on it maybe later on in the...
So we haven't said anything about mathematical inquiry. We said what math is.
Yeah.
But now we have to tell the viewers what mathematical inquiry is, which is where Tara's question comes in. So let's erase this and give a brief sense of what mathematical inquiry includes, beyond, of course, making calculations. So if this is what math is, then we should create axioms, and we should create definitions. Right? This is one part of mathematics. Another part is guess conjectures. This is what the famous mathematician Ramanujan was famous for.
So you mean about the objects you define?
Conjectures which are likely to be true.
About the objects you define in the world.
That's right.
Which is these axioms.
With those axioms and definitions.
And that world is it's a world that has come out of your imagination.
Imagination, exactly. So this is a part of the creativity of the mathematician.
Yeah.
People tend to think that mathematicians are not creative, imaginative people. That's hardly true. Mathematics is probably the most imaginative of all subjects. And then you prove them. And then you create theorems. That is the other part of mathematics. Guessing conjectures and proving them as theorems. And the third is the one that Tara mentioned, mathematical modeling of the real world. So, for example, Galileo, in order to state his laws about the world, used Euclidean geometry. Newton used Euclidean geometry and calculus. Yeah. So these are examples of mathematical modeling.
So I'm looking at this and thinking, high imagination, rigorous reasoning, and then application.
Okay,
right?
Imagination, and this part requires rigorous reasoning.
However, each step of a proof also requires a significant amount of imagination.
Yeah.
Yes.
And to guess conjectures,
absolutely,
you need insight.
And then mathematical modeling involves all of these.
All of
it,
those,
yes.
yeah. So those are the mental capacities that you need in order to do mathematics. Oh, somewhere here, I forgot to mention calculation. That is also part of mathematics, but we are not going to pay a great deal of attention to that.
Yeah, but that's not necessarily a separate thing. That's involved in your proof.
Sometimes in the proof, or sometimes in this
the
modeling and so on.
So it's not. It doesn't fit in this list. It's outside of this list.
No, sometimes to prove something,
in order to prove
something, in order to apply, you need to calculate.
Yeah.
So let us recognize calculation as a legitimate but very small enterprise.
Yeah.
Right? And most people think of math as this. That's why I wanted to
not
reject it completely, but saying it's a very small part.